And by the way, I'm going to apologize in advance that the handwriting on the notes, on the lecture notes that I'm going to publish is not as great as it usually is. I don't know why, but anyway, so let's say that we have a system where the net torque is not zero. It turns out that it's still possible for the moment of inertia, and the angular speed to be unchanged. And so you might wonder how that works, because torque, according to Newton's second law, should just be equal to I omega. But the trick here is the way I've written this, right? Importantly, torque is a vector, omega is also a vector, but notice that I wrote angular speed, i.e. omega without the vector. So recall that torque is actually dl dt, right? That's a different version of Newton's second law. And importantly, this is a vector equation. Somebody's mic is on, by the way. I'm going to mute you. And the important part about this equation, and omega, or L is equal to I omega, the important part about this equation is that omega can change direction without changing magnitude. And so it can be the case that omega, the vector, the angular velocity, is changing, while the magnitude of the angular velocity, the angular speed, is unchanged. Think like circular motion, for example. So I actually want to show you a video on gyroscopic precession. This is a video from Veritasium, so if any of you guys have seen something like this, or this video in particular, it's a good video. I think I'll just play the whole thing because it's only 3 minutes or so. And then I'll stop and write a few things down. So let me stop the share. Let me share a different screen. Hopefully this will play through for you guys. So
from the channel Veritasium, and I've been following this series by
Let me know if
Destin on
it's
Smarter every
not
day about
going.
helicopters. And gyroscopic precession is just one of those things that still blows my mind, as it did Destin. So I'm here at the University of Sydney, my old stomping grounds. I'm going to borrow some of their lecture dem equipment to hopefully teach you a bit about how gyroscopic precession works. The first thing I need to do is talk about vectors, because a lot of things in physics are vectors.
Pause. Let me send the link to on Discord really quick. Although if you just search on YouTube gyroscopic precession, this is the first video that pops up. So, but I'll send it. So what I'll do is I'll play the video, and if you want to watch it on your own, you should have plenty of time to watch the majority of it.
That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction, and if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum
don't know why
will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance
By the
from the
way,
rotating
this is
axis.
wrong. He's acknowledged this. He has it in the
force applied times
flipped
the radius
order.
away from the
It should be
turning
R
axis.
cross F, not F cross R.
Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a
I don't know why it keeps doing this.
very large angular momentum out towards the camera, out towards you. Now, before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go.
Sorry, I'm going to
And if I let go,
quality.
because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get my head cut off by a bicycle wheel. So.
All right, so that was that. It's an excellent video if you and he has another video on this sort of thing as well. If you want to check it out later, it would be linked in the sidebar if you want to watch the sequel. So the bottom line is that if you have a non-zero torque that's perpendicular to the angular momentum, you'll get rotational, or you will get motion that's called precession, or it's kind of like orbiting. So let me draw a figure for you. God, this is so buggy right now. Okay, that's fine. So here we have, say we have a bike wheel, and it has two of these axes pointing out, and let's say one of them is balancing on like a pivot, right? So you're holding it in place initially. So we can think of this as a pivot point. I mean, you could have chosen any pivot point, but this is going to be a natural one. So let's draw some forces that are going to be present. So first of all, there's going to be a normal force pushing upwards from the pivot point on the wheel, right? Second, there's going to be a force that's pushing downwards from the center of mass of the wheel due to gravity. And that's, I mean, there could be friction and so on, and drag and all of that business, but for the most part, that's basically everything. Now let's say we give this this wheel, and this is just like a bike wheel, by the way. Whatever. Say we give the wheel some speed, omega, angular velocity. Well, if I've drawn this properly, the angular momentum, imagine that like this side of the board is closer, or that side of the wheel is closer. If I've drawn that properly, then the angular momentum, and you can check this with your right-hand rule, should point to the right in this picture. Trying to draw it in 3 dimensions is kind of tricky. Now, let's figure out what the torque is from the normal force. Well, we're going to use that point, the point of contact between the fulcrum and the axis. We're going to call that the pivot point. So the normal force for that particular the torque for that particular force is just 0. It's the 0 vector, and that's because the normal force is applied at the location of the pivot. However, the torque due to gravity due to the force of gravity, well, that's not applied at the pivot point. And in fact, it depends on two things. It depends on both the magnitude of gravity, and it depends on this distance here. Call that, what are we going to call it? I want to call it capital R. That's the distance from the pivot to the center of the wheel. And so that the magnitude of that particular torque would be, oops, it's doing this thing that I hate it when it does, would be R cross F. Now they're perpendicular to each other, so it's just the product of the magnitudes, and then we use the right-hand rule to find the direction. So it'd be R times mg, and then the direction would be into the screen. So the way that we depict that is with a circle with an X, and that's because it like looks like the back of an arrow. So like imagine an arrow pointing into the screen or into the screen. It would have its feathers in the back, and you would see that little X. So this is into the screen. So importantly, in this setup, the torque vector is perpendicular to the L vector. L points to the right, and the torque points inward. So you can see that they are perpendicular. So now we can use the angular impulse momentum theorem, and we can start to analyze this. So the angular impulse momentum theorem is this equation. It's that the change in angular momentum is the torque times the duration over which that torque is applied. And so importantly, this implies that the torque vector points in the same direction as the change in L. Somebody's mic is unmuted, and it's muted again. So the point is if you want to figure out the difference between a final L and an initial L over some small chunk of time, that will be a vector that points in a direction, and it points in the same direction as the torque vector. So in this case, if torque is into the page, or is into, yeah, well, I'll call it the page. That means that LF, which is it's the angular momentum after a small amount of time after the initial case. This would be Li plus delta L, where this is into the page. This Li, this is to the right. And so that means after you add these vectors together, you would get a vector that's mostly to the right and a little into the page. And so what does that look like? Well, it looks like this is happening. So the vector starts out to the right, and then it rotates a little bit, so that now it's still mostly to the right, but also slightly into the page. And so this will keep happening. And so the angular momentum vector goes around in a circle. And what does that mean? Well, the angular momentum vector tells you via the right-hand rule what direction or what the orientation of the wheel is, because the wheel is spinning. And so if the wheel is spinning like this, let me make sure I get this right. The wheel would be spinning like this. Now I should use the right-hand rule. Yeah, so the wheel's spinning like this from your perspective. As it moves, it's still spinning. And so in order for the angular momentum to point into the page later, it has to still be spinning. So that means that the whole wheel has to be rotating, has to be going around in an orbit like you saw in the video. And so what this means is that the wheel precesses, and I can never remember how many S's there are. I think it's that, precesses in a circle. So, and this is called gyroscopic precession. This phenomenon where you have a spinning object with a perpendicular torque applied, that object rotating is called gyroscopic precession. So we can do some analysis of how this actually works fairly straightforwardly. So for example, we can try to calculate how long it takes for the gyroscope, in this case it's just a spinning wheel, to make a full rotation. And by one full rotation, I mean how long does it take to go all the way around, not for it to spin once. A spinning object with perpendicular torque, with a torque that's perpendicular to its angular momentum. This is one full rotation take for a gyroscope. So before we actually do this calculation, we're going to argue by analogy. So let's consider regular circular motion. Regular circular motion, we can figure out the period of rotation. So you have an object, and then you have another object that's going around that axis. And so for this, and maybe it's going this way. It's just, you're just swinging a rock tied to a string. That's the standard example. So let's look at the various vectors that are associated with this rock in this case. So at this moment in time, we have our object. The force, we know what direction the force has to be in. Because it's undergoing circular motion, there's centripetal acceleration. That means that the acceleration of the object is towards the center of the circle. It's this direction. And so that has to be the direction of the force. So the force is in this direction. And because it's moving this way, at least at that instant in time, its momentum, P, is in this direction. And so you could do the same thing over here. In this orientation, the force is this way, and the momentum is this way. So an important point, just like how we had precession, or just like for gyroscopic precession, for regular circular motion, the momentum and the force are perpendicular, rather than the torque and the angular momentum. So we can use this feature to try to understand the rate of a single orbit or a single precession. So let's just start writing down some equations and stuff will pop out. So the force, the magnitude of the force, is equal to the mass times the centripetal acceleration. Now, the centripetal acceleration, we already know a formula for. It's v squared over r, where this distance is r. And now we can do some algebra to this, and we would get that this is mv times 1 over r times v. All I did was I split up the variables. But mv is equal to the magnitude of the momentum. So this is p over r. Well, let me write it a different way. It's p times 1 over r times, well, the velocity. We know that if it's moving at a constant rate in a circle, we know that the amount of time it takes to go in a constant rate, or to go at a constant rate, is just the total, we can, the total distance covered is 2 pi r. The speed is v, so we can just divide them. So in this case, we would write that v is equal to 2 pi r over t. Here, t is the period, or the duration of a single orbit. And so, again, rearranging, this is p times 2 pi over t. So that means, so remember, we started off with force is equal to this thing. So that means that we can solve for the period of a single orbit. The period of a single orbit, then, is 2 pi times p divided by f. So that's just for regular circular motion, and you could check that that has to be true. Just write down the, you can check that that's true if you do the math more explicitly than this, but this sort of argument works. So we can use that argument to relate to what happens for gyroscopic precession, or gyroscopic motion, rather. Because a lot of the same features or a lot of the features for regular circular motion are present. You have some momentum vector, you have some sort of force vector that are perpendicular to each other, you have circular motion, and so on. So again, we have our point, or our axis of rotation. It's just this time, we have a wheel that's spinning, and it's going around in a circle. Because of gyroscopic precession. Terrible circles, I'm sorry. So let's assume that the wheel is spinning this way. Actually, let's assume it's spinning the other way. Yeah. So let's do the same thing that we did up here. We drew the momentum vector and the force vector. Here, it's not momentum and force, it's angular momentum and torque. So we have our wheel initially in this configuration. So its angular momentum should be that way. You can use the right-hand rule. Imagine that, let me draw this a little bit better. Trying to draw in 3D is kind of tricky. So imagine that this is the closer side. That's the easiest I can do, or that's the best I can do. So that's the direction of the angular momentum vector. What direction is the torque? Well, the torque is, I would use, so right-hand rule. So you guys can use the right-hand rule. I'm going to use the right-hand rule off screen, so then I can determine the torque. But importantly, the force is, it's hard to draw in 3D. This is the direction of the force though, right? It's the force of gravity acting at the center of mass of the wheel. And so the torque is this direction. And then we could do the same over here. We have angular momentum this way, torque this way. And so again, we find that the momentum vector, in this case it's a rotational momentum, is perpendicular to the force vector, in this case a rotational force or torque. And so we can use the same argument for rotational, or that we use for circular motion. Just as in circular motion, the period, t, for one full revolution is 2 pi times the magnitude of L over the magnitude of the torque. And so we can just work this out explicitly. For a hoop, this is a wheel. A hoop might be a technical term for a wheel. Just imagine it's like a ring rather than like a solid disc. With axis of length r. So that's the that's this distance here. We can actually compute the angular momentum and the torque. So the torque is just the distance times the force, and they're at right angles, so the magnitude of the torque is just the distance times the force. The angular momentum, we need to know what I is, and we would need to know what omega is, but omega might be given. For a hoop, the angular momentum about the center is just mr squared, where hoop has radius r. Capital R. So that means that the period, not lowercase t, which is 2 pi times I omega over the distance times the force, which is just mg times little r. That is just mr squared omega, sorry, I'm missing a 2 pi. 2 pi mr squared omega over mgr, which is 2 pi r squared omega over gr. And so this is not a trivial result. Like, this is kind of like, this is the answer here is complicated, but this is indeed the result that you get if you try to figure out how long it takes to go about in an orbit, or to process one full rotation. So a lot of what the bottom line of what we did here is we basically just reasoned using the same way as circular motion. Now you could do this explicitly, work out exactly the rate of change of the angle as a function of the angular momentum and so on, and that will work, and I'm more than happy to go over that in office hours. But it's simple enough to just argue by analogy, which works perfectly well. All right, so we only have 15 minutes left, but I might have to run a few minutes over, if only because I want to make sure that I cover everything that that you guys need for the homework. So we're going to start a completely new topic. We're done with angular motion. I mean, angular motion always comes back to bite you, but we're done talking about it now. What is happening? Go away. Okay, we're going to talk about gravity in more detail than we've done before. So there are a few questions that we might have. Is the torque? Yeah, the torque is the force times the distance, because the distance vector r is perpendicular to the force vector f. So because they're perpendicular, the torque is just r times f, the magnitude anyway. So there are some questions that you guys may have had about gravity that we never actually covered. I kind of just brushed them under the rug. So first, why is the force of gravity equal to mg? Like, why is that? Where does that formula come from? Second, how does that relate to the? How does that force relate to the way planets move, for example? Because we know gravity does both things, so how are they related? And then the third question is, how does gravity work? Like, you have two things that aren't touching, how do they influence each other? Now, in the remainder of this course, or in the next few lectures, we'll be able to answer the first two fairly straightforwardly. Unfortunately, the third one, I don't really know the answer to. Nobody really does. We have ideas, but you know, it's an open question. So let's answer the first two then. So first, I need to introduce you to another of Newton's famous laws. This is Newton's law of universal gravitation. And by the way, everything I'm about to tell you about Newton's gravitational force, it's not technically correct. It's a very, very good approximation for small masses, i.e. masses that we encounter on a daily basis, up to masses of stars and so on, and for low speeds. But you have to, but the approximation gets worse and worse as the things that are traveling move faster or as the masses get larger. So Newton's universal law of gravitation can really be summarized in like 3 bullet points. First, gravity is a force that acts between two objects. That you should have already known. But importantly, it's only two. So if you want to find all of the gravitational forces between a whole bunch of different objects, you have to find the gravitational force between every pair of objects. Second, gravity is always attractive. There's no anti-gravity. There's no negative mass. Third, the magnitude depends on only two things. The magnitude of the force. The masses of the objects, and the distance between the objects. And the way that it varies with the distance is via an inverse square law. So there are some consequences of these 3 bullet points that are fairly straightforward to derive. So I will do that. So the first is that, I'm not going to write this down, but it's in the notes, is just that Newton's third law applies, right? So if the Earth pulls on an apple with a force of, say, 500 newtons, the apple also pulls on the Earth with the same 500 newtons. Newton's third law still applies to the Newton's law of universal gravitation. But the real consequences come from the third bullet point, which tells us how the magnitude changes with various parameters. So first, the magnitude of the force of gravity is proportional to the product of the masses, m1 and m2. So if you double the mass of one of the objects, the gravitational force between the two objects doubles. If you double the mass of both objects, the gravitational force between the two objects quadruples, right? This tells us that there's a proportionality there. A second relationship is that the force of gravity goes as the inverse, or is proportional to the inverse of the distance, of the square of the distance between the two objects. So this r here is the distance between the two objects in question. So if you double the distance between the two objects, the force goes down by a factor of 4. If you triple the distance between the two objects, the force goes down by a factor of 9, and so on. And so we can combine these formulas to get another proportionality. We get that the force of gravity is inverse, or is proportional to m1 times m2 divided by r squared. And so we're almost there. These are the only things that affect the magnitude of the force. So all we need to do in order to get an equality is replace the proportionality with a constant times the terms in the proportionality. So what we get is we get that the magnitude of the gravitational force, that's not what an F looks like, and it is a vector still, by the way, all we've been talking about is the magnitude here, is some number, call it g, times m1, m2, divided by r squared. Now g is just a constant of proportionality. It's just the number that makes this thing true. And it turns out that g is a quantity that can be measured. It's about 6.67 times 10 to the minus 11, and then the units that it has, because it has units, because this has units of newtons, this has units of mass squared over distance squared, so we need to fix that. It's newtons times meters squared per kilogram squared. That just is that just happens to be the number that gives us the constant proportionality for gravity in our universe. And it's a small number, by the way. Like notice it's not particularly large. So that tells us the magnitude of the force between the gravitational force between two objects. What about the direction? Well, the direction was already hidden in the properties that Newton's law of universal gravitation told us. It's always attractive. So what that means is that it points to the center of mass of the attractive or of the attracting object. So if you have two objects, the force on one will be towards the other, and the force on the other will be towards the one. So I'll give an example just to kind of make this less abstract. So consider the first object is the source of the gravity. And this is just an arbitrary distinction I'm making, like they both apply force equally to each other, but we're just for the sake of imagination to understand this better. So consider the first object of a pair of masses. Say one of them is the source. We want to make that the origin of the coordinate system. So if we were to draw a coordinate system, some coordinate axes, the first object would be here. That would be the source. And regardless of how that object's moving, we're just going to imagine that our coordinate system is moving with it. Let's say that you have another object over here, which is the recipient of the force. Now, again, they both apply a force to each other, but we're only considering the force on the recipient right now. So there would be a gravitational attraction between these two objects, assuming they have mass. So let's consider this vector r hat. It's the vector that points from the origin to the object or to the recipient and has unit length. So in this case, r hat it's the unit vector pointing away from the source. And that's because the source was located at the origin. So this is the trick that we often do. We just make one of the objects the origin so that the other one, so that the vector r hat points away from the other object. But importantly, this is the unit vector for the position vector of the recipient. So you would take the position vector of the recipient, and that position vector would be this vector r, and you just divide it by its length, and that would give you r hat, right? And obviously this is coordinate system dependent. Like if you had chosen a different coordinate system, then the r vector is not necessarily the vector that points from the source to the recipient. But if you put the source at the origin, the r vector starts at the source and ends at the recipient. So it contains information both about direction, and i.e. the direction away from the source, and it contains information about the distance. So now we can ask the question, since it's attractive, what direction is toward the source? And remember, a direction is associated with a unit vector. So we would need a unit vector that points toward the source from the recipient. But that's an easy answer. It's just negative r hat. A negative sign flips the direction of a vector. And so this is a unit vector that points this way, which would be towards the source. And so that's the direction that the force points in, because the attractive force means that the force points towards the source. So what we can do then, come on, scroll for me, please, is we can combine this fact with the magnitude to write down a force equation, or a vector equation for the gravitational force. This is G times m1 times m2 over r squared. And here, by the way, this r is actually the vector r squared. It's the magnitude. If you dot it with itself, or if you take the magnitude and square it, that's what that r represents, times the vector r hat. That gives us the direction. So this is our standard equation for the force of gravity. Now, sometimes you'll see this with the minus sign brought out front. It's completely equivalent. I've just written it this way to indicate that this is the direction. Negative r hat always points towards the origin, and the stuff in front is the magnitude. Right, that's all great, but everything that we've just mentioned only applies to point masses. So if you have a complicated object, then it's not this straightforward. Question is how do we deal with extended objects? Because we should know how to do that. We know how to deal with extended objects using like torque and things now. So we should be able to do this sort of calculation for gravity. Unfortunately, that is beyond the requirements for this class. So we won't do it. It's just hard to do. It involves 3D integrals generally. Like it's not like conceptually difficult, but it requires math that you guys might not have. However, there is an exception to the above rule. For spherically symmetric objects, so it means that they're both shaped like a sphere and the mass is distributed symmetrically. For spherically symmetric objects, gravity acts as if all of the mass was at the center of mass of the object, and the object is a point mass. So if you take something that's perfect, if you take like a perfectly spherical ball, about how this works, yeah, I can. I'll talk about it in a little bit. But I just wanted to make sure I got this exception out of the way. Well, yeah, I have to keep going because there's a little bit more that I want to get to. Oh boy. Actually, no, this is fine. So the point is if you have like a solid spherical ball, gravity would act on it and come from it as if all of its mass were concentrated at a point at its center. So, for example, both the sun and the Earth are both approximately spheres. I know. Oh no, I'm not out of time. It's still 10 minutes. So the above is a good approximation, and I'll draw a picture here. So this whole business with point masses is a pretty good approximation for what happens for the sun and the Earth. So the picture here is you might have the sun, and then you have the Earth, obviously not drawn to scale. The sun has its center of mass here. The Earth has its center of mass here. And so the distance between them that you would calculate would be this distance. And the masses that you would use would be the masses of those two objects. So you could calculate the magnitude of the force between them just by figuring out the distance between the center of masses of the sun and the earth. And that might be given to you, or maybe you look it up, and then multiply the masses, divide by that distance squared, and multiply by this magic number g. That will give you some number in newtons, which is the magnitude of the force between the earth and the sun. And it'll be a pretty large number because they're both very large. But so this is all great. Like this is, I've kind of gone over a lot, I've told you a lot of things, but you guys have this idea of gravity in your head. Gravity's just mg downwards. So I need to clarify and explain how Fg being equal to negative gm1 m2 over r squared in the r hat direction relates to Fg, call this F grav, is just minus mg in the j hat direction, right? Like how are these two they're clearly very different. How are they the same thing? How can we call them both gravity? So the reason why they seem so different is because one is an approximation of the other. So in principle, to calculate the force of gravity from the Earth on some object, we need to know three things. There are three numbers that we need to know. So first, we need the mass of the Earth. That's something that clearly will come up because that's one of the terms. Second, we need to know the mass of the object. And third, we need to know the distance between their center of masses. So the reason why we can assume our second object, not the Earth, is spherical is because it's not even, or the reason why we can use this calculation, this formula, for any object near the surface of the Earth is because all of the objects are so infinitesimally small compared to the size of the Earth. It's effectively a point mass when we're talking about the Earth. So it's a fine approximation to treat basically anything as a point mass when we're talking about gravity. And that's why, by the way, when we were talking about like some extended rod, gravity acts as if it's from the center of mass, because that's what gravity does for objects that are approximately spherical. And when objects are very, very small, they're, at least relative to the size of the Earth, they are approximately spherical. So once we know those three things, then we can write the magnitude of the force of gravity is g, that's just a number that stays the same, times the mass of the Earth times the mass of the object divided by that distance squared, right? So now you can ask, how do we get F sub g equals mg from this? And it's actually fairly straightforward. We just start plugging things in. So for any object on the Earth, or for any object experiencing the gravity of the Earth, the number g times me is always the same. Right? It's just the mass of the Earth times the gravitational constant. And then you're going to multiply that by the mass of the object divided by the distance squared. But this will always show up if you're trying to find the gravitational pull from the Earth on an object. And that combination of numbers has a name. Come on, scroll. It's called the gravitational parameter of the Earth. The reason it has this name is because before people knew what the mass of the Earth was and what the mass and what g was separately, they knew this gravitational parameter. This is just a thing that could be measured without having to know either one of them independently. No. So minus mg is an approximation of gmm over r squared. So the gravitational parameter of the Earth is just, it's g times the mass of the Earth And it's just the number 3.986. Again, this is an approximation, but it's a decent one. Times meters, or times 10 to the 14th meters cubed per second squared. It's just a number. Sometimes you'll also see it called mu sub e. I don't know why. It's just just something that people decided to do 250 years ago. Okay, so right away, our formula simplifies to just this number, 3.986 times 10 to the 14th meters cubed per second squared, times the mass of the object divided by r squared. Secondly, on the surface of the Earth, the distance between the center of mass of the Earth and the object is basically just the radius of the Earth. That value r, it's approximately the radius of the Earth. And that's because the radius of the Earth is very, very large compared to like 10 meters. So if you hold something 10 meters up, that distance isn't any different up here than it is down here. Like it's very, very small. So this being r sub e being the radius of the Earth. And so the radius of the Earth, again, it's just a known quantity. It's about 6.378 times 10 to the 6th meters. And so we can use both of these values, mu sub e and r sub e, to get an approximation for the gravitational force on an object. So for any object with mass m on the surface of the Earth or near the surface of the Earth, we can compute the magnitude of the gravitational force. It's g times me times the mass of the object divided by the radius of the Earth squared. And so plugging this in, you just get or simplifying, you get g me over re squared times m. That's just a number that you can compute now. All of those things are given to you. So this is 3.986 times 10 to the 14th divided by 6.378 squared times 10 to the 12th times mass. And there are units here, by the way. This is the units of mu sub e divided by r squared. Well, we can actually look at that. So if you take the units of the gravitational parameter, it's meters cubed divided by seconds squared. So if you divide by meters squared, you get meters per second squared. So this is meters per second squared times m. By the way, this is an acceleration. That shouldn't be surprising. And so just plugging this in, you get that this is 0.098 times 10 squared meters per second squared times m, or approximately 10 meters per second squared times m. And let me write meters out again so then it's not confused with the mass. And this number here, this is g. So the magnitude, after plugging in the mass of the Earth, the distance from the center of the Earth to wherever the object is, its radius, and the gravitational constant, combining all of those things and factoring out the mass of the object just leaves you with g, the mass of just leaves you with mg. Now, just as a thing for you guys to think about, I won't actually write it down, but for you guys to think about. So let's say you have two objects that fall from the same height. They fall, we can observationally note that they have the same acceleration. So perhaps you guys should think about why that has to be the case. Now, we are out of time. I want to just briefly go over one more thing. So maybe give me 5 minutes. So another question that or a concern that you might have is, well, that's fine and dandy if an object is sitting at the surface of the Earth, but what if you throw an object upwards, for example, like in projectile motion? wouldn't that change the force because the distance from the center of the Earth to the object is changing? And so the acceleration really wouldn't be constant? Well, you can figure that out for yourself. So the way that you would do that is, and so yes, the bottom line is that yes, the acceleration basically is actually constant. Let's say that you can throw a ball up. Let's say you can throw a ball up 10 kilometers, which is like the cruising altitude of a jet plane, right? That you might say, oh, well, that's really far, so its acceleration should change significantly. But let's actually calculate and check. So the acceleration is different at 10 kilometers above the surface than it is at the surface, but it's useful to check how different it is. So the distance that the object is from the center of the Earth would be at 10 kilometers, would be the distance of, oh, I don't need a vector symbol, would be the radius of the Earth plus 10 kilometers, right? And so you could calculate the force of gravity, and it would work out to be 9.77 meters per second squared times m. And this is as opposed to 9.80 meters per second squared. Like it's clearly not very big. And in fact, even if you just use 10, meters per second squared, that's only different from either of these values by just over 2%, which is a very small amount, and friction will ruin your accuracy far before 2%. So the point is if you just use 10 meters per second for any reasonable like height that you're going to, any small height relative to the radius of the Earth, 10 kilometers relative to 6,378, it's going to have a negligible effect on the actual acceleration. So we can just assume it's constant and you will have a good approximation of what actually happens. You could try this also with the altitude for the International Space Station. That orbits at about 400 kilometers above the surface of the Earth. And so you would find that actually the acceleration of gravity or the acceleration that an object would feel 400 kilometers up is about 8.7-ish meters per second squared. So it is smaller by about, I don't know, 12% or so. But it's like you have to get very far away from the Earth in order for the acceleration that an object would feel drops significantly. So I'm going to end it there.